Hi, my name is Maddie Gaines, and this is my Physics 2212 Lab 4 Circuits. The purpose of this lab was to use the physics principles of the conservation of energy in order to predict the behavior that circuits have containing different resistors and capacitors, observing said behavior through the use of an online model and using multimers to measure values of current and potential differences. In an ideal circuit, the fundamentals of this lab were conservation of energy and charge, Kirchhoff's circuit laws, which were the node rule and the loop rule, steady-state circuits, Ohm law, resistors and capacitors in series and parallel, capacitance, and time dependence and resistor-capacitor circuits. With regards to my results, I found the actual values of current voltage given by the model matched those predicted by the formulas, and that in an RC circuit, the magnitude of the current is time-dependent, based on an exponential equation. These are just some of the fundamental physics principles that I mentioned in the previous slide, displayed in their equation format on the slide. The system was our circuit, and the surroundings were everything else. In the ammeter configuration, we figured out that I1 was equal to I2, which was 0.102 amps, R1 was negative 0.959 volts, R2 was negative 2.041 volts. When replacing it with the voltmeter, we figured out that I was 0.02 amps and the potential difference was 3 volts. And with the closed circuit, we figured out the potential difference of the battery was 3 volts. The potential difference of 47 and 100 were negative 0.96 and negative 2.40, and the sum of the potential differences was 0. Then in the second experiment, we had a simulated capacitor at time t with two 1.5 volt batteries, emitters, and two light bulbs, which had 10 and 20 ohms as their recordings. We figured out that adding a voltmeter does not change the ammeter reading. This is because there's high resistance and not a lot of current flow. If the ammeter is connected in parallel with the 100 ohm resistor, both will show a 0.06 amp. For the circuit element resistor, R equals delta V over I, but the absolute value. We figured out that R47 for the resistor was 47 ohms, R for the 100 resistor was 100 ohms, R for the wire was 0 ohms, and R for the ammeter was also 0 ohms, and we can see the math displayed throughout the slide. The equipment we used in the RC circuit was a 9-volt battery, a 200 mF capacitor, a 10 ohm bulb, and a 20 ohm bulb. As the capacitor gets more charged, the lights dim. When the battery is first connected to the 10 ohm bulb, the capacitor is charging, current in the circuit decreases. Time for the capacitor to charge using the 10 ohm bulb was 7.6 seconds, the 20 ohm bulb was 14.15 seconds, and the time capacitor to discharge using the 10 ohm bulb was 8.9 seconds, and for the 20 ohm bulb, it was 16.7 seconds. The equipment we used for the new circuit was a 9-volt battery, a 200 mF capacitor, and a 30 ohm bulb. Plot from the data capacitor side for the RC, and to compute it was, the slope was negative 1 over RC, the slope was negative 0.166, the RC was 6.02, and the experiment took about 6 seconds to complete. Some possible sources of error were calculation error and human error for us. When comparing our data versus the model, the results from calculations and model differ slightly, but they're mostly similar, and idealized circuits will work better and differently than in real life. What if we were doing this lab in real life and used an actual ammeter instead of ideal simulated ammeter? We would recognize that our real results would have been lower due to the resistance that's in real life, and that is what's different about the real ammeter, and that's how it would have affected the circuits that we hooked it up to. If I was doing this lab in real life to use a real battery to charge a real capacitor with no resistor in the circuit, I would recognize that the capacitor would not have charged to its full capacity, and this is because the internal resistance inside of the capacitor would have stopped this. Our ideal model would be a lot quicker compared to the actual model. This prediction wouldn't really happen in real life. Thank you.